Hello. Okay. So, last time we implemented some softmax stuff. We added temperature, which made our neural network way less likely to quote verbatim from the training data. We changed our structure a little bit and implemented softmax in inner layers. The reason we had to do that is that before we were combining the softmax back propagation step with the gradient, or with the loss function, with the gradient of the loss function. So we couldn't actually use softmax in an inner layer. We needed a more complicated formula, which cancels out when it's in the output layer, but doesn't cancel out when it's in an inner layer. So we implemented that. It doesn't help us with anything yet, but on the left here, you can see this is what the transformer architecture looks like. And this is our eventual goal, to build a large language model out of this. Oh, I guess you can't see it here, but as part of the attention blocks, there's softmax in the inner layers. So we're not doing attention yet, but since we already had softmax, we were already doing softmax stuff, we just implemented that. Goals for today. I don't think we're going to get to layer norm. That's going to be hard. Residual layers I would like to do today. So that's these adds, easier to see in this diagram here. So that's when parts of the network skip some layers and then get added to other layers later, or to the output activations later. The other thing is reorganize / backward propagation. We're going to change up some of our code to be more similar to how PyTorch does it, where you've got a forward pass and a backwards pass. Because right now our backprop code is really assuming that every layer has weights and biases, basically. And that's not going to be the case once we add stuff like skip layers. So we're going to have to change and layer norm, or is it called? Yeah, layer norm. So in order to add, and it's already kind of not the case. Well, it's arguably not the case for softmax already. It's just that we combined softmax with a linear layer. And so that's and then we've just been calling that softmax with weights and biases. So we're going to split up linear from the rest of the layer types. We're going to have ReLUs be just a function that applies the ReLU function. And ReLUs themselves won't have weights and biases. That'll be linear. So anytime something has weights and biases, that'll be a linear layer, and then we'll have a ReLU layer that comes after it to recreate the network that we have now. So this is going to say input linear ReLU, linear ReLU, linear ReLU, linear softmax. That's what would recreate this same network in the new way that we're going to build it. So let's get going. So that's going to be a big change. So basically, this is going away. We're going to re-implement our neurons in a new format. So let's just get to it. We'll call this layers.py. Let's start with linear. So it has weights, np.nd array from or import numpy as np. It's got biases. It's going to have a forward. That's going to return activations. It's going to have a backward. That's going to return gradients. Returns activations. Returns gradients. We're going to have, an init, which can take an optional initializer. Self.weights equals initializer dot initialize self.biases. So we'll have to figure this out. And then I think we're also going to add save and load. And I don't know exactly how these will work yet. And this should simplify a lot of stuff once we rewrite everything to use this format. So why don't we from, or what am I trying to say? I'm trying to say, yeah, from typing import protocol, we'll have layer is a protocol. That just looks like this. Okay. So then we'll want to implement ReLU as well. And softmax, at least, in order to be able to use the, in order to run the networks that we've already been running so far. Okay. So if I go here, yes, network is not going to be initialized like this anymore. It's going to look something like this. I want to be able to use default initializers so that I don't have to say which type of initializer to use. I think this is still okay. It's just that I'm going to need linear ReLU, linear, whatever, like this. This would be an example of a of a network. I'm just trying to think really, or like, how should I do the numbers here? Because you need the number that comes before you as well in order to have the dimensions. So I don't know if I don't want to have to hard code that. I think this would be a better format. But ReLU doesn't really need to have a number of neurons because it's just applying a single function to whatever it's getting. So this one's a little different than the others. How does PyTorch do it? PyTorch, simple neural network. So for linear, they have input size. So you just have to repeat yourself. You say n by m, and then you repeat m by n. That's, I don't know. I don't like that, but I do like that you don't have to give a number for activation functions. And I like that the layer itself takes its own arguments instead of something else needing to initialize it later. I think I'll keep it like this for now, even though it's not, it has some disadvantages. I can't think of a simple solution to this thing. Well, all right, fine. I'll bite the bullet. Let's just do it the PyTorch way. So this is going to have to be, it's going to look like this. Input stops existing, and you just have, the first thing is linear with this input and this output. So you're gone. Then the next thing is just ReLU. Then the next thing is 800, 800, ReLU, like that. And then softmax, 800 to 87. So this is how you would define a network in this new model. I don't love it. I don't love that you have to repeat the sizes in subsequent layers, but there was downsides to both ways, so I'll live with it. Okay, so this is now going to be from layers, import linear, ReLU, and softmax. go over to layers. And let's implement linear. So the first thing is, right now we're saving weights and biases at the network level. We're not going to do that anymore. We don't have initializers. We don't have sizes. The only thing we're going to take is a list of layers, and these are layers. From layers, import layer. And it's a list of them. Self.layers equals layers. Okay, so that makes that a lot easier. We're gonna have to figure out how to do velocities. So let's pause on that for now. We'll have to come back to velocities. Okay. So how do you make a linear layer? We know that it takes 2 arguments, fan in and fan out. I don't know if there's better names for these. What does PyTorch call them? Oops. PyTorch. Initialize layer. Or yeah, just give me, what does linear look like? In features, out features. I haven't been using the word features. So, and I have been using fan in and fan out. So I'm going to keep fan in and fan out for now. So initializer is a weight initializer. Or none. From initializers, import weight initializer, and also import the other ones, like he and savior. Yeah, so you need to take a weight initializer or none. No, you don't need that. That doesn't have to be part of the definition. A layer can take nothing, but the linear layer is going to take these things. So weight initializer dot initialize takes fan in and fan out. So here's where we can say fan in, fan out. For biases, we haven't done bias initializers, so I'm just going to hard code it. And it looks like this. But it's just once. So it's fan out, comma 1. Okay, we're initializing a linear layer now. Oh wait, this I said or none. So if initializer, or I can just do initializer equals initializer or HE. And I'm guessing that got deleted. HE. So for linear layers, the default will be HE or he. I don't know how to pronounce it. Good. Okay. Forward. This is just going to be what is apply doing right now? Apply. It just looks like this, but just for a single layer. So you're going to go here. You need the activations of the previous layer, which we've been calling X. This temperature thing only applies to softmax. And then we're splitting up the function thing. So we're just returning this. Self.weights times X plus self.biases. And we should have a self here. So you need self, you need activations of the last layer. Okay. This is all linear does. All right. Return gradients. So here's where it's a little weird. I think I want to return. There's 3 gradients to return. There's the thing we've been calling delta. There's the gradient of the weights. And there's the gradient of the biases. So I can't just immediately update my weights and biases here because I might want to do momentum stuff. Well, I guess I could do the momentum inside here, but I'm thinking momentum is something you would probably want to control outside of this. And this should just tell you the gradients. So so it should be something like this. And then if I take a look at how we're doing the back prop right now. So you do the forward propagation and you remember the Z's and the X's. In this new world, there's no difference between Z's and X's. They're both activations. Like the Z was the activation. You can think of the Z as the activation of the linear layer, which becomes the input to the activation, or to the activation function layer. So Z's and X's are not separate things. They're all they're all the same thing, which is activations. Because now we've split the layer in 2. So so this is gradient of W, or here. I'm returning gradient of W for all of them, gradient of B for all of them. Instead, I'm going to do it layer by layer. So this is the gradient of W for a single layer. And this is the gradient of B for a single layer, which is the same as the gradient of the loss function with respect to the inputs, the activation. So delta equals this. Delta, you're just delta, you're delta. Self.neurons.j is not a thing. We are the neuron. So what was the neuron doing to get the delta? This is a linear. So this was the delta. Go back over here. So delta is this thing. F prime was 1, right? Neurons. F prime is just 1. Okay. So this goes away, and it's just this. W is self dot weights. Deltas of 0 is the delta that's coming from the layer in front. So we don't have that here. We'll have to take that. np.ndArray. And I'll just call this D because I don't want to confuse it with the delta that came from the next layer. And then what's this? This is the activation. So this is this. So I'm just going to say you take that as an argument. A is np.ndArray. You take the delta, you take the activation. And then we're just going to have a framework that does the forward passes, remembers the values, and passes them back into the backwards passes. Okay. Save and load, we can do these now. Self, you should just need self and maybe file name. You need that for both of them. How was I doing? So np.save and then an nd array. So it's going to look like this. np.save. Oh, maybe we should have a file descriptor passed down. Is that what it's called? What's the type of that? Fname write bytes. Supports write bytes. What's supports write? Oh, I don't know what those things are. I'm just going to leave it untyped, I guess. F self.weights. f self.biases, and then load and b.loadf. Self.weights equals this. Self.biases equals this. And I just need to do them in the same order. Okay. Pretty cool. I think this is good. So now let's do linear. Or sorry, we just did linear. Let's do ReLU. So you don't take any parameters, and you don't have you don't need to init at all. You also don't need to save and load. Forward is you just apply the ReLU function. So looks like this. This is X. Backward, you're going to have to return delta. Which is going to look like this, f prime. Times the other delta, right? How did I do delta here? Oh, now I'm confused. Who's in charge of multiplying the deltas? Is it this, or is it the thing outside of here? I think it's this, because here I'm matrix multiplying my delta. F prime is this, F prime times delta. I'm not sure if this is right. We'll have to see. And then there's no other gradients. There's nothing else to learn. We just need to figure out the delta so we can keep passing it backwards. Okay, then softmax is going to look more like ReLU than like the other stuff now. Except it kind of takes a temperature. Which is just a number. Self.temperature equals temperature. And if you don't provide one, it's just 1. There's nothing to save or load. Well, actually the temperature could be saved and loaded. Self.temperature. Like, this is weird though, because temperature is not part of the model. It's part of the application. So I think I'm actually going to take temperature out. forward looks like this. Z is called X. Backwards looks like this. Okay, so X is called A. Deltas of 0 is called delta. And we don't have this. This is what we're doing in the linear layer that comes before it, if a linear layer comes before it. Where is that? Here, weights transpose matrix multiplied by delta. So this is not, basically we don't have E anymore, we just have delta. Yeah, I think this is how it works. Because the softmax is not being combined with a linear layer anymore. Though the softmax does... Well, actually, that's a good question. Here I was saying that the softmax needs to have a dimensions, but it kind of doesn't. It's this linear layer that needs that. So it should look like that. Then temperature kind of comes in here. Temperature float equals 1.0. I don't really know how to deal with arguments that come at runtime, but this is going to be how it works in this thing. So Z is going to be equal to X times temperature. Like this. Okay. And you don't need to take temperature into account when doing the backpropagation. Okay, softmax, ReLU, linear. Backward, I said you need delta, np.nd array, and you need activations, np.nd array. Oh, and you don't return this, you return a dictionary that maps strings to ND arrays. Okay, so then network looks like this. When you go into network, you take a list of layers. Good. Save is going to look different. Save is basically going to be this is a little weird because now I don't have the shape anymore, but let's just assume that the shape is correct in the, well, actually I think I can do it like this. I'll just have to fix how the layer stuff works. So this will be with open for layer in self.layers layer.saveF, and then load yeah, the thing is I don't have layers to iterate over yet. So here's what I want to do. Self dot layers equals layer dot load for layer in self.layers, which doesn't make any sense because I don't have the layers yet. So I'm going to have to start by saving the structure and then load the structure, and then for each thing in the structure load a layer for it. This is also a class method. So, okay. You make a net with nothing. You add layers to that net. And then at the end, you return that net. Load here should be a class method. Class method. Then we want to initialize, we want to do like class layer equals this layer.weights.biases return layer. I don't care about the fan in and stuff. Undefined name class, yes, class. Yeah, this is it. Nothing else has anything to save, right? No, okay. So you're supposed to be a class method. Copy that for view. Okay, and yeah, you're already good. So load for layer in something. How do I get the layers? I just need to know what type they are. I don't need to know anything else. So why don't we start by saving that? Layer classes equals np.load f. Allow pickle equals true. Okay, then we just need to start by saving those. So np.save. Oh, and then you also do like dot item, right? Let me do something dangerous and control Z a bunch until I get to what it used to be. Yeah, you do dot item. Okay. np.save f, and then the thing you're saving. Is that how it works? Yes. So type of L for L in self.layers. La. So I save all the types, and then for each layer I save itself. Then I load the types. And then for each just call this CLS. No, I can't call it that. Just call it layer CLS. So now I'm manually setting the layers, and then I'm returning that net. Okay, I think that's right. Now apply is going to be different. It's going to be simpler. We don't have weights and biases in neurons. It's just going to be x equals or it'll be for layer in self.layers, x equals layer dot apply, or we call that forward x, return x at the end. We can still do our temperature thing. So if layer is self.layers, if it's the last one, layer.forward, and this is an else. Here, why don't I do it like this? This is annoying. So do everything except the last layer is what I'm trying to say. I think that looks like that. Python 1, 2, 3, 4 up to -1, 1, 2. Okay, so everything except the last layer. you just do this. And then at the end, you pass in temperature. But only if it takes a temperature. How do I check that? Python check if function takes argument. Ugh. I don't want to do anything like that. I'm just going to do this, and we'll just comment it out if for some reason our output layer doesn't take a temperature. Okay, that's apply. Train is going to need a lot of changes. So let's just go through it piece by piece. This is the same. Shuffle the training data. You make a batch. You update with a batch. Okay, so train is exactly the same. So let's go into update mini batch. This is going to be totally different. So we do need to store gradients. We don't know what gradients we're going to need to store until we're done with the backpropagation, but that's okay. Because we're not modifying them. We're just like collecting them one at a time. So let's not know what they are in advance. Like I'm wondering, why do we even initialize them as 0 when we never modify them? I think these could have just been setting them. Like basically appending to the list right here. I think this would be the same thing. If these things were like that. Okay, but we're not going to know what, we're just going to have a bunch of gradients. Grads equals a list. Then this is tough to do each piece in isolation. The reshaping thing is weird. I think reshaping should be the responsibility of the layer itself. So let's make sure we're doing that. This should be dot reshape self dot biases dot shape, and with a sum first, right? np dot sum axis equals 1. Is that the same for the delta? I don't know, I'm getting a little confused now. I don't think it's the same for the delta. I think only the biases need to be reshaped. But why would that be the case? Because we need the matrix deltas while we're doing the backprop, I believe. But I'm not sure. I am a little confused. So we'll see if it works. Okay. So where were we? So we want all the gradients and we don't care what they are. Backprop is going to return gradients. So maybe this can be delta grads. This should be per layer. For layer in layers. We're just collecting more, or what is it we're doing here? So this, we don't need the sum thing anymore, because now we are doing that inside the layer somewhere. So this can just be the same as the other one. What am I doing here? I think this is weird because of when we changed from doing mini batches one at a time to doing them in bulk, because we're kind of not doing anything here now that we're doing them in bulk. We're basically not doing anything. We just get the gradients. Okay. Then this is long gone. We want to do the velocity thing. We want to keep that. We want to keep the regularization. Which means that we actually need to know which do we need to know which like learnable parameters are which so that we know which ones to regularize? We don't have self.weights and self.biases anymore. Each layer has its own thing. This, whenever I see this, this should be 4 layer in self.layers. This doesn't exactly make sense. Well, I mean, this doesn't make sense. Or it would just be layer.weights. So to do, how to tell what to regularize. I think we probably still want to save the velocities outside here, but I'm not sure about that. Maybe each layer should be in charge of its own velocities. No, I don't think they should. I think we want the velocities out here. These are the gradients. We're not going to have W and B velocities anymore. We're just going to have velocities. It's not going to be of I, but I am not sure how we'll know which one is which. And then here's where you have to actually update the thing. So layer dot weights. Okay. Maybe once we fix backprop, this is going to be easier to figure out what to do. So we don't have Z's anymore. We just have X's. Forward propagation, it doesn't look like this anymore. It goes 4 layer in self.layers. You still need to make this big B. No. Did I do that in the layer? I didn't. This is a difference between application and forward propagation, which I didn't think there would be. Because the biases needs to be, we need to stack them as many wide as X is. I think we could just do that in the layer. So yeah, self.biases, then B. And that should work when X is a vector also. Possibly, hopefully. To do, does this still work when X is a vector? We'll find out. Okay, so you don't have to do that out here anymore. You don't do this. You just append, and this is X's. And we don't need to remember it outside here. So it's just layer dot forward X, like the last one. Okay, that's forward propagation. Backward propagation is basically for layer in self.layers reversed. So starting from the end, layer dot backward. This needs delta and A. Delta L. Do we need to remember the deltas? Yes, we do need all of them. There is something different about the final layer, right? I'm not sure if there is actually. So I'm thinking you do something like, and this will all be deleted soon. Deltas equals empty list, but it starts with this, right? Grad L X. Can I give this a better name? That's fine. So that's the first delta. First meaning the one on the end of the list. And we're going to keep inserting them to the front. So deltas equals delta star deltas. So the first delta in the list is the next one in order. So that we want to take the next one and bring it forwards through the list, like leftwards. Okay, but backward returns more than just delta. It also returns all the gradients. So delta equals grads of delta, which is the only one we know will be there. Okay, let me try to think about this in a different way. We've got all the grads, and these are layer by layer, it's dictionaries. So it's a list of dict from string to end arrays. Starting with this. So the output layer's delta looks like this. Or maybe this is the layer after the output layer, I'm not sure. Okay, then as we go backwards, Python insert to front. L equals 1, 2, 3. L dot insert 4, 0. L. Okay, L dot insert 0, 5. L. Okay, so I can do grads dot insert 0, this. Grads of 0, delta. Okay. This is hard to think about now, but so at each layer, this thing has gradients, and it's got delta, which is the one that needs to go forward, and it's got others, which are learnable parameters. Okay. So that's that. Wait, we were saying the first delta is delta uppercase L, which is this times the output delta, which ended up being 1 almost all the time. So let's just keep this. So we've got all our gradients, we've got our grad W's, even though they're not in the same format as before. This stuff is already being done. This stuff's already being done. Okay, then this used to return gradients for W and B, but now it's going to return all of the gradients. So list of dict of string np.nd array. Okay. So backprop returns all of the gradients. We don't care about the deltas. We care about everything that isn't delta now. So for grad in grads, I'm still not sure how to tell what to regularize. Why don't we zip layer grad in zip self.layers and grads. So I don't know how to do this part yet. If layer dot weights, if has attribute layer weights. This is no good. We have to change this, but that's what the to do is for. Okay. Velocities. Are stored globally. Where am I storing them? So we got rid of all this. But we still need velocities. 1 second. We don't know what the learnable parameters are until the first backprop. So velocities is going to start as empty. So what is layers? Layers is a list of layer. What is velocities? It's a list of np.nd arrays. So for grad in, well, we already called the dictionary grad. Why don't we call this all grads? This is grads, and then this will be for name grad in grads.items. Self.velocities of name times equals mu. Velocities of name minus equals this. You're just called grad. And then finally, layer, how do I do plus equals on a thing where I don't know the, where I don't know the name of it? It's going to be like layer.get or get attribute layer name plus equals this, but I don't know if you're allowed to do that. How do you do that? Python assignment after get attribute. Could do set attribute. Let's just do that. Set attribute layer name, and well, the problem is it's the, then I have to get attribute. I have to do it like that. Okay, I guess that's what they're doing here. They, as in the AI overview. Param equals this. Actually, I wonder if I can just say param equals get attribute. Param plus equals this. That's nicer. Hopefully I'm not modifying a copy of it, but I don't think I would be. Okay, now velocities needs to be a dictionary. Well, even this needs to be like a tuple. With like layer.id comma name, which is just weird, but velocities is a dictionary that maps tuples to ND arrays, and I will not specify what kind of tuples. I probably should. Is hash a type? Actually, I don't know this. What's the type of, or here, class layer pass la equals layer la.id. Oh, I meant hash of la. For some reason I thought objects always came with a .id, but you have to do a hash on there. What's the type of hash of la? Int. Okay. Velocities. So it's a tuple from int and string. Okay. And it's not name, it's this. So let's just call this key. Okay. Okay. It looks pretty now, kind of. I'm updating delta, which I shouldn't do. If name equals delta, continue. We need those while we're back propagating. We don't need them when we're updating stuff. So update learnable parameters. Okay, what are the chances this works? 0%? Am I hearing 0%? Python main. It's just so much code changing in one go. I'm amazed it hasn't crashed yet. It's probably loading the data still. Okay. Backward, missing one positional argument. Backward. I'm passing in the delta, but I'm not passing in the activations. So this is why I remembered the X's. Zip X's layers and pass X there. Try that again. That's what backwards takes, right? First delta, then X. Zip is not reversible. Come on, just do it anyway. Cast the zip to a list. Just want to confirm backwards takes delta and then activation. Good. Okay. The reshape thing is not working, which makes sense because of how confused I was while I was writing it. Can I reshape an array of size 800 into shape 87.1? So how should I... I'm not sure which layer this is in, so I'm going to reduce the number of layers just to try again. I'm getting confused now because my format's a little different and I'm not used to it yet. Why am I trying to reshape an array of size 800? Print delta.shape a.shape self.biases.shape. Oh. No, I don't think that matters. Okay, start by just printing stuff. Let's just see what it says. Delta is 87 by 50. A is 800 by 50. Bias is 87 by 1. So am I sending in the wrong activation? I think I might be off by 1 in which activations I'm sending into backward. So do you skip the first one? $87.50, $87.50, $87.1. So that one looks good, and then the next one, or it can't be the next one because it didn't print something new. So why am I still trying to reshape something of size 800? Biases.shape, self.weights.shape. My weights are 87 by 800. Just want to print all of this stuff. I want D, and I want delta. All right, just print me everything. Delta is 87 by 50. A is 87 by 50. I'm guessing this is this layer here, because it's the first one that I would go to during the backpropagation after softmax, which won't print anything. So activation is 87 by 50, which makes sense. Biases is 87 by 1, which makes sense. Weights is 87 by 800, which is confusing. And D is 800 by 50. Shouldn't weights be 800 by 87? I wonder if I am just initializing it wrong. Initialize is supposed to take fan in and then fan out. But then we're doing fan out, comma, fan in. I wonder if I just had this backwards. Okay, I'm going crazy here. So you have an M by N matrix multiplying a N by P matrix. That's going to give you a M by P, which means the number on the left or multiplying a vector n by 1, which means you end up with the number on the left. So the number on the left should be 87, and it is. Okay, so that part's working. Delta is this. D is 800 by 50. I don't think 50 is supposed to be there in D at this point. Because the batch size shouldn't matter in the end. I'm not sure. I guess I would expect D to be 87 by 50. And then we sum along one axis to get the biases to just be 87 by 1. I have to pull up the textbook, Nielsen Deep Learning. Show me the equations of backpropagation. Okay. So the B's are the deltas. The B is the delta. I'm just trying to reshape it into the right shape. The weights, the gradient of the weights is activation of the previous layer times delta. Wait, show me the matrix version of these. Maybe that's not in here. Okay, I just have to think about it carefully then. A times delta of this layer. D is what I'm calling delta of this layer. Delta is what I'm calling delta of the previous layer. Or of the next layer, I mean. So A times delta, this is an A times a delta. Possibly... this is probably right. Maybe it needs to be like A times D instead of D times A, but let's say this is right. Delta is weights of the next layer transposed times delta of the next layer. Here I have weights of this layer times delta of the next layer. And then it's times sigmoid, which I am not including because I'm splitting the activation from the linear layer. Let me just check. When I do ReLU, where is ReLU? Here. Okay, yeah, that's when I'm multiplying by the next delta. Do I have this all wrong? Multiplying by the next delta. I don't know if that's right. Multiplied by the next delta. The problem here is on this left side here, they're doing the linear and the activation function as one step. They're saying delta of this layer is equal to weights of next layer times delta of next layer times sigmoid prime of this layer's activation. I've split the layers in two, where I put the activation function on a layer that comes after the linear layer. So this part comes after this part. But the thing that's confusing me is this part is grabbing stuff from the layer after it. Which I think just means I have to think of passing the delta through on the ReLU so that it's available here as a delta. Okay. I kind of think what I'm doing makes sense, but it's like not sharp in my mind. So I'm having trouble picturing which things need to be which shapes. D is ending up 800 by 50. But I don't think 50 should be part of the dimension. But I'm not sure. So we're collecting the grads on the way backwards. Delta is 87 by 50. Weights is 87 by 800. When you transpose weights, it becomes 800 by 87. I wonder if I should be transposing delta instead so that we end up with 87 by 800. Well, even still, we wouldn't be able to just take the bias as the delta. I wonder if this bias is supposed to be the input delta. Actually, maybe this would make more sense now that I think about it. I also wonder if the weight should be the input delta. I actually don't know. I would think they would be using the same delta. And then this is like delta L minus 1, kind of. Okay, so what's my new problem? List indices. Okay, but velocities is not a list. Oh, here. Key error. That makes sense. We don't know what the velocities are the first time we go through. So here. How do I deal with that? I only want to do the velocity scaling if I have a velocity. If key in self dot velocities. Well, no. What I want to do is if key not in, you can be unindented. Self dot velocities of key equals np dot zeros grad dot shape. Okay. Plus equals the velocity. Operands could not be broadcast together. Why are there 3 different things here? There's only 2 sides to this, I would think. So print player name. Param.shape, self.velocities key.shape. Oh, I printed the whole layer. I didn't mean to print that. I meant to print, well, whatever, it's fine. Okay, so we've got our a linear layer here. The name is weights, so we're trying to update the weights, which is an 800 by 1740. So that must be the first layer. That would be this one over here. Ooh, right here. And velocities is 800 by 800. So I think we're just off by one because this layer, oh no, actually no layer should be 800 by 800. Okay, so we've just got a bad print grad dot or yeah, print grad dot, or I've already printed grad dot shape, but I'm assuming my grad dot shape here is wrong. Grad shouldn't be 800 by 800. I haven't actually printed grad dot shape yet, but I think the zeros are getting set to the wrong size. 800 by 800. Okay, so our weights are the wrong size here. Maybe that does mean this one's supposed to be D and not delta. It's too bad I'm so confused about what comes from this layer versus the next layer versus the last layer. So what's the issue now? These look like the right shapes now. It's just that it's backwards. So what about a dot t at d? Oh, wait, I can't do that. Shouldn't I be able to do that though? I'm printing all of this stuff, so let's take a look at it. Delta is 87 by 50. Activation is 87 by 50. Biases is 87 by 1. Weights is 87 by 800. And lowercase d is 800 by 50. I don't think 50 should show up in lowercase d. Well, I guess I'm grabbing 50 from the next layer, so maybe it does. Okay, then that D looks right, actually. If the next layer is 87, then this one should be 800. Wait, I'm just confused about why. Well, I guess I did just change that. This should be back to how it was a second ago. Okay. 800, 1740, 1740, 800. So the weights are 800, 1740. That's right. And then 1740, 800, that's wrong. So how did the velocities end up with a different shape? If I look at network velocities, the velocities, I mean, I can just do this. I am just kind of confused about why I ended up needing to do that. My gradients are not the same, are like the transpose of my bias. Okay, let's stop that. We're able to get through without errors, which is miraculous. Let's remove our print statements. And I just want to make sure we're training something relatively small. Let's do 10 characters. And then not 800. I'm getting lost now. We don't need this anymore. Let's not do 800, let's do 80. Hidden neurons. I just want to see learning. I expect it to be 45% after the first epoch if it's working the same as before. Ah. True, we didn't really finish doing that, did we? Forward. Oh, this does take temperature. Oh, we tried to pass that into a linear layer? How did that happen? Temperature. Oh, because I removed the last layer, but here I'm just doing layer instead of self.layers of -1. How long did it take last time? We can't tell. Question mark seconds. Network has no attribute layer. That's true, but what's... Oh my god, so layers. Okay, this should work this time, right? I fixed one bug, so it's guaranteed to work. If we see 45% after the first epoch, then it's working. Okay, 16%. That's pretty disappointing because it means it's learning. It did learn, but it didn't learn as much as it's supposed to. Because in our old way of doing it, if we had this, this should be the same as the old way. This would get us 45% after the first epoch. So what could cause it to learn but not well? I don't know. That's going to be hard to figure out. We can stop that. Looks like gibberish. It's not obvious to me that it learned anything at all. But we do see it do 1% when it learns nothing at all. I guess this is not the right type of initializer. It's not that it matters. It barely made a difference before. Initializer equals Xavier. Initializer equals, that's already the default. It's just the softmax layer where changing the initializer brought us to 46% after the first epoch. So that's not going to be the difference. We already were expecting 45%. I guess we confirmed that this still works, probably. This is a crazy way to do it, though. I should have just done x.shape 0, not length of x0. But that's not going to fix anything. That can only break things. Indeed. Does shape 1, I guess, actually. We're not getting any overflows or anything, because that's another thing that happens when that can cause us to have bugs. It's so confusing that it would work but not well. I'm just looking at it and trying to see if there's anything that could cause that, but I can't think of anything that could even, in principle, do that. Hum, 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 hum. I'm thinking I should have called this D and this delta. Keep it more in line with the rest of the parameters and the return things. You're a D, you're a delta, you're a delta, you're a delta, you're a D. Okay, well, it is crazy that weights and biases are not using the same variable. That can't be right. Can it? It shouldn't be. These are the same in this equation. So what if you used delta? Just want to also change this. And then on the calling side, it shouldn't matter. Back, what did I call it? Backward. Yeah, I don't even pass a name. Pass it by name. Okay. This just won't work, right? It'll just be the wrong dimensions. This is so weird. Because there's no way these are supposed to be using different deltas. I'm guessing this is not the right shape. Print D dot shape and this guy dot shape and weights dot shape. D dot shape is 80 by 50. D is the delta of the next layer. 80 by 50. So we managed to go backwards through both layers. So the first one was 87 by 50. Okay, then we're saying that our weights are a square matrix, which they should not be. D, give me delta also. D is this, delta dot shape. Okay, so delta is the error that's propagating to the previous layer, the layer before this one. We're going to send it backwards. So it makes sense that the next one is 87 and this one is 80, because 87 is the last one and 80 is the middle one. It also makes sense that the weights are 87 by 80. My weight gradient should also be 87 by 80. You're the weights. And the activations are going to be they should be 80 by 50. And then let's print that and make sure. Oh yeah, 87 by 50 in the second one and 80 by 50 in the first one. 87 by 50. Okay. I'm trying to peer into the matrix here. D is 87 by 50, same shape as A. What we want is for our weights to be this, the gradient of our weights to be the same shape as our weights, which is 87 by 80. I don't know why I am getting to the point where I just have to write down really simple stuff, or I can't hold it in my head all at once. So that's not even a thing what I just wrote. Okay, A looks like this. 87 by 80. Weights, so W is 87 by 8, or sorry, A can't be by 80. A has to be by 50. Weights is 87 by 80. D is 80 by 50. And delta is delta, the third one, 80 by 50. Wait, D and delta are the same? No, I got one of these wrong. D is 87 by 50. In the last layer, this is. Okay, so I have to combine this stuff into something that's 87 by 80. I want the 50s to go away and the and the 87 to be at the front. Okay. So I have to have 80 at the end so that the 80 can be, or I have to have W at the end so that the 80 is preserved. So something times here. Something times something times W. I can transpose either A or D here. So let's say A transpose. And then in the middle, I have the other one, so D. So this would be, no, you can't transpose the outer one. You have to transpose the middle one. So this would be 87 times, or 87 by 50 times 50 by 87. No, this isn't going to work. I have to use delta in order to get a W, an 80. But that's the messed up part, because now the bias is going to be using a different delta. It's so confusing. Because they should, it looks like they should be using the same delta in the same layer. But my bias needs to be 87,1, which means it needs to be 87 something. So I have to use this lowercase delta, since the bias is just the delta. But I can't use this. Okay, if I did use this, I would have to use the activation of the previous layer here. Which is really confusing. So, but let's say that that's what we want to do. So let's say this was the activation of the previous layer. That would mean this is 80, which would mean I want to do D times A of the previous layer. So that would be 80 by 50 times 50 by 80 which gives you 80 by 80 times W. I'd have to put the W at the front. $87 by 80. Oh, I'm going crazy. It doesn't fit. I don't know how to make it fit. It's not that hard. I just am having trouble here. Let me move this A out of the way. So I'm trying to find this, which is just activations times delta. So why am I trying to do three things together? I shouldn't have to put the weight in there. That's already there when figuring out delta. So this delta is 80 times 50. I need this A previous and the lowercase d. So it would be D yes, it would be this. If I could take the correct A. Okay. But that means I have to be passing a different activation into here. I can't be passing this X. I have to pass the previous one, which means I don't want to skip the first one. I'm crossing my fingers as hard as I can. Um, 80 by 870 and 80 by 80. I'm still ending up with an 80 by 80. After all I've done for you. D is 87 by 50. A is this now. So transpose is 50 by 80. So I should end up with 87 by 80 as my weights. Let's start printing shapes again. So oh wait, it's training. No, it's not working properly. But it was 1%, which is how you know it's broken. This is working. Hold on. Don't print. Why was it working? Why does it continue instead of crashing? So it's overflowing in layers line 108. So in the softmax, in the backwards of the softmax. Oh, but it doesn't really need to be doing this. When it's the final layer. When it's the final layer, you can just say delta equals D. Let me just do that temporarily. No overflows. If this says 45, we are officially cooking. It should say 46 actually, because now we've got the right initialization on the softmax layer. Xavier initialization. 46. Oh, baby. That looks like English. It's not English, but it looks like English. Okay. So we have this issue where the backwards pass is different depending on whether it's the final layer or not. If I go look at our training, oh yeah, we still have to do this. We'll get to that in a minute. I'm just happy we got back to where we were. All right, when do we do backwards? Over here. And now I'm saying that backwards is always the same, but I kind of want the backwards on the final layer. I don't know how to say this. It's just that if I combine the cost function. Okay, let me say what I'm trying to say instead of stopping my sentences short every time. The cost function is the thing that you're supposed to pass as the first, or the gradient of the cost function is supposed to be the first delta. Because we're doing cross entropy and softmax, we know that they cancel out so that you don't have to do the first backwards pass of the softmax. So I guess I could how do I does that mean I can just skip the first layer? So you reverse the layers, or the last layer. This would be the last layer at this point. And then if I brought back my accurate delta, it's just that this is kind of cheating, but oops. It's weird and cheating. I don't like doing this. And it's going to confuse me later, which is the most important thing. Okay, so here we have a list. Here we skip the last layer. And then, yeah, that's still a complicated softmax. So now we should be able to have a softmax in the beginning or in the end. And we're always just skipping the last layer, which only works if the last layer is something that can be skipped, like an activation function or a softmax. Okay, that's back to working. So let's leave a big comment here because this is confusing hell. We skipped the last layer because we're assuming cross entropy plus grad, or it's not plus, cross entropy or grad of a loss function where we're assuming grad of the loss function equals x minus y. We're assuming we picked a loss function such that its grad on the final layer is equal to x minus y. Okay. Now we're above 50%. What does that look like? Hello. It looks like English. And what if we grab the first line of dialogue from the game? If you haven't been paying attention, we're training on the dialogue of Final Fantasy VII instead of using any kind of normal English corpus. Is Barrett Presidgens Shatalnitawit? That's a right, Skitikui. I'd saddened it. That vo. It's cool. It's cool. Okay. All right. So we can check this off. We did our first goal. We haven't gotten to residual layers yet. I think we should be able to do that now. So I don't know what to call it. A skip layer, a residual layer? Residual layer. What does PyTorch call it? Maybe they don't have a thing for it. All right, let's call it a skip layer. So what am I trying to do here? I want to do something like this. So a bunch of, when you have a lot of layers, using skip layers is a way to solve the vanishing gradient problem. These shouldn't all have this initializer, just the last one. And a skip layer is like you take the output of this and you bring it forwards and you add it to this. Though I actually am not sure now that, okay, yeah. So we would say like skip, or maybe skip. So this would be like skip 4. This would be skip 4 ahead, and this is skip 4 behind. It shouldn't be called skip, it should be called add. Maybe skip and add. Or add from skip layer. Add from skip. So then I'll just take the activation from 4 behind, maybe 6 behind. 1, 2, 3, 4, 5, 6. One, 2, 3, 4, 5, 6. Wait, I'm getting confused here. Seven? How did I end up with an odd number? 1, 2, 3, 4, 5, 6, 7. Because I want to grab it from here. Let's just say 6. Because you already grabbed the one from here. Okay, it's kind of hard to do this in a network the way that I have it laid out, because because you need it from both sides, right? When you're going forwards, at this point here, you need to know that you're grabbing something from farther behind. When you're going backwards, it's at this point here that you need to grab the gradient from further ahead. So the way I've seen other people do this, I think, is to basically define a layer. You would say like class skip def forwards def backwards. This is starting to get confusing. It's basically like you grab this stuff and you say like skip and then you have this stuff here. This is what I'm trying to say, and failing horribly. Then this guy still has a forward and a backward. It's just that inside its forward and backward, it goes through its own block of stuff. Are they called skip layers? Skip layer neural network. Yeah, okay. So this is what we're doing. Okay, let's see if we can get this working. Skip. Import skip. Go to layers. Let's add. Well, why don't we copy softmax? Call this skip. You've got a pretty complicated init because you take layers, list of layer, self.layers equals layers. If you're going to save, you have to save all of your layers. For a layer in self.layers, layer.saveF. If you're going to load, you have to load all your layers. Oh, this kind of breaks our thing, our save and load thing, actually. Because we can't just grab the layer classes anymore. We need to know what those inner layers were. It's a tree now. We have like a whole graph, not just a list. To do fix, save, and load so that layer classes is a tree/graph instead of a list. Okay, for layer in self.layers, layer.load. Oh, wait. Oh, yeah. This is the problem. I can't do this. Okay, so to do. Forward is for layer in self.layers, layer.forward, x temperature, which, I mean, it would be crazy to pass temperature into this. You don't need a, actually, it doesn't even make sense to pass temperature into that. Okay, we're running into a problem immediately, which is that we're not going to have the activations for the backwards pass. To do, we don't save the activations for the backwards pass. And then backward doesn't look like this at all. It just looks like grads is a thing for a layer in self.layers going backwards. It's like we want to copy. Where is it? We need to do all this stuff, and it's not straightforward. We might need even more general, we might need to generalize our update mini batch even further. Because we can't just get attribute when we've got a bunch of stuff on the inside here with different attributes. Or like we have a bunch of different layers with weights. So we can't just get attribute and update the weights. We could override get attribute though. Get attribute. To be like for layer in self.layers if get attribute layer name return attribute. That's craziness, but I think that works. Then we just need to make our names unique. Make names unique. So backward. It's like we have to do this again, right? It's this, I guess. I don't have this though. I don't need to start it with anything. Well, I guess I need to start it with D. We don't get to skip the last layer. And we don't have the activations. However, self.cache equals empty list self.cache.append x I don't remember if it's the first one or the last one that we don't need. It must be the last one. And then here, instead of grabbing, we don't have XS, but we do have self.cache. So this is let's call this all grads, all grads, all grads, all grads, grads, grads equals this. We want to, all grads. We want to rename them so that the get attribute can find them. So it's not actually going to be this. It's going to be it's going to be something like this. Is there a way to rename key Python dict? You have to pop it and add it? Okay. So for key val in grads dot items. Or let's just make new grads. Okay. For key val, this is so crazy what we're doing, but whatever. New grads at key f of layer hash of layer slash key equals val. Okay, so I've made the names unique, and now to grab them, let's move this to the bottom. It's not that you want to go for layer. You take the name, you split it on slash. You're going to have the layer hash and the name. If layer hash equals hash of layer. Then you return the get attribute. Okay. Well, hold on. This is gonna break stuff, actually. Because now I can't do like dot forward. It's not gonna be able to find that. Unless I add... what happens if you can't split? abc.split on slash. Okay. Well, what if I did a comma b equals this? Not enough values to unpack. Try this. Accept value error. Return super get attribute. Name. Okay. Ugh. So what is this craziness? Get an attribute from a sublayer, from any sublayer. It's actually an attribute of this class. To do, we don't save the activations. That's not true. Now we do. We cache them. What are the possible odds that this works? So right now, skip doesn't do anything. It just like, I might as well call this block. Well, does this work? I'm sure the answer is no, but why doesn't it work? Yes, fair enough. We don't have an overall delta at the end. We could just keep replacing delta. How do I... how was I passing delta already? Oh, okay. Okay, well, this is the same. Okay. It's like I want to pop everything except delta. So I'm just going to end up adding delta back. Delta equals grads of delta. That's not the right place to do that. I should do that out here. I can just do it here, actually. Delta grads of delta. What's the problem here? All grads is a list. Network line 118. Oh, it's not supposed to be a list here. Here it's supposed to be just this big dictionary. So I guess you could just have this be all grads. Not have new grads. But just continually overwrite delta. All grads of delta equals grads of delta at each step. Yes, it's not a list anymore. Just grab the key called delta, which is the currently last delta, or first, because we're going backwards. So why didn't velocities get initialized here? No, that's not the issue. The issue is that get attribute probably didn't find the attribute. Print layer name. It is the skip layer, and that looks right. Wait, why are we looking for delta? We shouldn't be looking for delta. Oh. Oh. We don't need to be updating the deltas. Okay, same error. This time it looks like we just couldn't find the attribute for some reason. So Why not? Is get attribute being called? Start with that. Yes. Is it finding the layer? Probably not. Print hash of layer for layer in self.layers. And print layer hash and name, and then exit. That's this. So why didn't it find it? Or maybe it did find it, but at some point it stops working. Let's get rid of the exit so that it at least crashes on the right one. Yeah, so this is this. Okay. Print found it, layer, name. You get attribute, layer name. Just the type of it, because I don't want to print a giant matrix. We never said found it. Why? It's right there. Is this some weird Python thing? Class A pass A equals A, hash of A equals hash of A. True. So why? Oh, type of hash of A, int. Hash of A equals string of hash of A. Okay, we're comparing a string to an integer. We got this. We got this. Okay, kill. Stop printing stuff. I think we have more print statements around here. Yep. How would we know if it's working? It would be if I guess it would be hard to tell because we've got layers before and after. Like this is a really deep network. So I don't even know what to expect because we've never tested this before. 45. I think it's probably working because it's taking longer than it would if the middle layers weren't there. Oh, and it is really good. Okay. Goals. Fix. Saves load for residual layers. Now, we can actually implement the residual layer, aka the skip layer, aka the add layer. Where did I hide it? Skip. Okay. So the idea is that when you go forward, initial equals x, then you return x plus initial. So you do the whole block and then you add the input back to it. So that's the forward pass. And then on the backwards pass, you add the delta from the beginning to the delta from the end. So right at the end, you would say all grads of delta equals all grads of delta plus initial delta, which is D. D. Plus equals D. I think that's it. I think this is everything you need to do for a skip layer. How would we know if it worked? Well, we've never done this before, but since the point of a skip layer is supposed to be to solve the vanishing gradient problem, I would hope to see it learn faster. So a second ago, when skip was not implemented, and this was basically just a block, we got 45, I think, percent on the first epoch, and then 49 on the second epoch. 47 on the first epoch. That's better. So I think we can say it's learning faster. I mean, we only did one test, but the test is consistent with this working, which is crazy, considering how mixed up I was getting while I was implementing it. Epoch number 2, will it be better than 49%? No, it's still 49%. So it's hard to tell if it's working. It's at least not broken. But yeah, in theory, we should be able to train like really deep neural networks by doing this basically. Well, so let's say 800, 800. And then just having a bunch of these blocks. Now this is a crazy network because this is gigantic. But yeah, that's the idea. So let's kill this. Say hello. It looks like English, which means it's working. Oh, saving and loading is not going to work. But we kind of implemented residual layers. Oh, overflow. Why did we overflow? I don't know. But let's stop it because it's probably not going to work after an overflow. Kind of want to bring all the 800s to 80 just so that it has a chance of running before we end the stream. 47. It's pretty good for, well, yeah, let's stop it, say hello. Looks English E. And then if I had the same thing but without the skips, it should also work, but it should learn slower. So instead of having 47.17 on the first epoch, we're expecting it to be less. So are they skipping a ReLU here? It doesn't really matter because that's not the part that's hard to train, but I'm curious if there's a reason why you wouldn't want one. $45, okay. So we did it. We implemented skip layers. They are helping us train faster. They're solving the vanishing gradient problem. So I'm going to end it there. Thanks for watching, and I hope this was helpful.